So today's lesson is all about logical shifts. So we're continuing the Data 2 topic. And let's see, here we go. So today's learning objective, we need to be able to use logical shifts going right and left and understand what they do. So it's all about multiplying and dividing. Multiplication is quite a long process for processors. It's quite slow. Addition and subtraction you can do in one clock tick. So if you have a CPU that works at 1 gigahertz, the gigahertz means 1 billion clock ticks per second. So a clock tick is just going from 0 to 1 and back again. It's like a little prod, an electronic prod that makes the CPU do something. And in one clock tick, if your CPU is set up right, it should be able to execute one simple instruction. But although the instructions can cope with some pretty complex stuff, they can do addition and subtraction and all sorts of other things, multiplication takes a lot longer for a CPU to do, except for simple multiplication, like multiplication by 2 or division by 2. So we'll work out how we can do that with logical shifts today. So we've already talked about binary arithmetic, and we've said that it's exactly the same as column arithmetic in maths. So we'll just have a quick recap of how it works. So a quick recap of binary addition. If you have a binary number and then you have another binary number and we want to add them together, first of all, if this is stored in 2's complement, which one of these numbers is positive and which one is negative, and how do we know? So we've just had it confirmed that the first bit in 2's complement tells us whether or not it is positive or negative. And so we know that this is a positive value and this is a negative value. If we want to add them up, let's check and see if we remember how to do this. So we start on the right with the least significant bit, and we go 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0, and 0 plus 1 is 1. So let's check and see if we've got it right. So we're going to convert each of these 3 rows into denary. Now I've said we're using 2's complement at the moment. So our bit values, how do we change colour in this program? Let's have a look. Let's go red. Start on the right, and they double in value, and that's going to be really important for our logical shifts. Oh, have I forgotten a bit here? 1, 2, 4, 8, 16, 32, 64. Yeah, I've forgotten a bit, haven't I? Oh well, we'll do it with 2's complement 7-bit, previously never seen before. So 2's complement just means you take the most significant bit, which should have been minus 128 if I'd actually counted properly, but it's early in the morning, never mind, and we make it negative. Right, so let's work out. We have 8 plus 2 is 10, and we have 16 plus 1 is 17, and then we do minus 64 plus 17. So we're expecting this to be 10 minus 47. What's that going to be in denary? So it should be minus 37, and let's check and see if we've got it right. First of all, it is going to be a negative number because the most significant bit in 2's complement tells us it's negative. And then we're going to have minus 64. Let's do this in a calculator. 1 plus 2 plus 8 plus 16 minus 64 is minus 37. It works. Good. So that's a reminder of our addition and our subtraction. Logical shifts work, or they use that principle of the bit values increasing by a value of 2 as we shift across to the left. Resume. So here we go, logical left shifting. All that means is you take each bit and you shift it across to the right or to the left, and you pad with zeros. So let's give some examples. If you go right, you do the same. Each bit just shifts across to the right, and you pad with zeros. So I think we should do some examples here. So let's hopefully have an 8-bit number this time. Let's go back to black. 1, 2, 3, 4, 5, 6, 7, 8. So we've got an 8-bit number. If we want a logical shift left by 1 place, that means that all of the bits just get shunted across to the left. So I'm going to pause the video in a moment. What do you think will happen to the denary value if we shift one place to the left? So the prediction is that it will double. Let's have a look and see if that's true. So that 0 moves here. That goes there, and then a 1, and then 2 zeros, and a 1, and a 0. And that, let's do this in a different colour, that gets lost. It's disappeared. We haven't got anything to go here, so we have to just pad it with zeros. Right, now let's work out what the values are. We've got 1, 2, 4, 8, 16, 32, 64, and minus 128. But for logical shifts don't really work with negative numbers. They only work with unsigned integers. So we're going to stick with just our normal 128. We'll deal with arithmetic shifts, which do work with negative numbers, next time. So we're just dealing with unsigned positive numbers. So what have we got? 4 plus 32 should be 36. And then if our prediction is right, we should double that to get 72, yes? Let's have a look. 64 plus 8 is 72. It works. So if we shift left, we double. Okay, predict what happens if we take the same number, so 0, 0, 1, 0, 0, 1, 0, 0, and we do a logical shift one space to the right. What will happen? So our prediction is it's going to be dividing by 2. So we'll just write out the same number, 0, 0, 1, 0, 0, 1, 0. Where are we? That one gets lost, and we have to pad in an extra 0 on the left. So that original one, that top one was 36. Half of 36, I think, is 18. My maths is bad, but hopefully it's not that bad. Nobody's disagreeing with me. That's good. Right, so let's try again. We have 2 plus 16 is 18. Fab. So the point here, if you shift right, you divide by 2. If you shift left, you multiply by 2. But there's one slight complication. What happens if we have an odd number? Now, here's another question, a related question. How do we know if a number is odd or even just by looking at it? Think about it and then try and answer it when I put this on. 1, 2, 3, 4, 5, 6, 7, 8. So is this number odd or even? Great. So we've just had a prediction that this is an odd number because we have a 1 as the least significant bit. And I think you're absolutely right. So if we shift to the right now, we're still going to divide by 2. But if you divide an odd number by 2, you get like something 0.5. So we need to work out what happens. So we should probably work out what this value is. Value holders. So 1, 2, 4, 8, 16, 32, 64, and 128. We've got some maths to do. So what have we got? 32 plus 8 is 40. 40 plus 128 is 168. 170, 171. Does anyone disagree with me? Because you're probably right. Good. Okay. So let's shift one space, a logical shift to the right by 1. That one gets lost. And so we just shift it across. 1, 0, 1, 0, 1, 0, 1. And then we pad with zeros on either side. So let's have a think. If we predict, what do we think 171 divided by 2 is? Let's pause. So our prediction is 85.5. But it's an integer. It's an unsigned integer. Now in maths, if you have a 0.5, you're going to round up, aren't you? But integer division, you always round down. So be predicting which of those you think are going to happen. Is it going to be rounding up, like maths? Is it going to be rounding down? I'm not going to pause. Let's work out what it is. So let's see. 1 plus 5 plus 16 plus 64 is 85. So when you do a logical shift to the right, you divide by 2. But if it's a 0.5, you always round down. So it truncates. It does not round. It gets rid of. So that extra 0.5 gets lost. Why does it get lost? Because we got rid of that one bit there. Okay. So what I would like you to do, is open up on the VLE Year 10 O2P8 and work through activity 1 And it tells you which direction and what type of shift. So these are logical shifts. I'll do the first one with you. Denary value before shift, 11. Binary pattern before shift, so we've got to have an 8-bit number for 11. So let's think. That's going to be 8 plus 2 plus 1. So 8, not 4, but 2 and 1. Ooh, I can't type. See? 8. Come on. 8, not 4, but 2 and 1. And then 4 bits in front. Binary pattern after shift, we're just going to go left by 1 space. So 1, 0, 1, 1, 0, and then 3 bits in front. And then we hope that that's going to be doubled, so it should be 22. And I'd like you to try and work these out. So let's see, that should be 2 plus 4 is 6. And then 6, not plus 8, but plus 16 is 22. It works. Fab. Make sure that you write these down as 8-bit numbers without any spaces between the nibbles, please. So we're going to go through that one again, but this time showing the working out. The question said we have a denary value of 11. Help, let's go in a sensible colour. We have to first of all say the binary pattern before the shift. So let's work out the bit values, 1, 2, 4, 8, 16, 32, 64, and it's a logical shift, so we only can deal with unsigned integers. Let's go up to 128. In order to get 11, I'm going to add 8 plus 2 plus 1, and then zeros everywhere else. Then we do our shift. Now this question is talking about a shift left by 1 space, and it's a logical shift. What does that mean? It means everything is shunted across to the left. So we have 1, 2, 3 zeros, 1, 0, 1, 1. And then we have an extra space, and in a logical shift, we just fill those spaces on either side with a 0. So let's now work out what that is. We've got 16 plus 4 is 20. 20 plus 2 is 22, and that has worked. That's great. Shifting to the left means doubling. If we shift left twice, then we double twice, which means we multiply by 4. So I'm going to go through an example of activity 2. You've got the same numbers in denary, but this time we're doing a logical shift, so we're dealing with unsigned numbers, and we're going right by 1 position. So let's have a look. We've got a denary value of 11. So quick recap, you write out your bit values, 1, 2, 4, 8, 16, 32, 64, 128. And we work out which of those we need to add together to get 11. So 8 and 4 and 1. All of the rest are zeros. So that's your binary pattern before shift. 4 zeros, 1, 1, 0, 1. And then you do your shift. So we just shift it across with an extra 0 on the left because we're moving right. 0, 0, 0, 0, 1, 1, 0. And then that 1 on the end has got lost. It's got nowhere to go. So the denary value after shift, well, 11 divided by 2 is 5.5. But remember, we always round down, so we're just going to have 5 here. Is any precision lost? Well, yes, it is, because actually 11 divided by 2 is 5.5, whereas oh, interesting. Have I done this wrong? Looks like I've got 6 here. What have I done wrong? Oh, because I've got the binary pattern wrong. Sorry about that, everybody. So let's try that again. So 11 is 8. 8 plus 2 plus 1, not 8 plus 4 plus 1. So when we shift that across, that's better. That's a 5. So precision lost means, did we have to round down? As in, did we lose a 1 there? So work your way through activity 1, activity 2. I'll pause the video, but do ask for help if you need it. So let's go through activity 3. You've got a binary pattern before the shift, and we need a logical left by 3 spaces. So let's just write this out with a bit more space. Why am I in orange? It's irritating. Let's go back. 0, 0, 0, 0, 1, 0, 0, 0. A logical shift left 3. So I'm going to draw some little jumpy things like 1, 2, 3. So that 0 moves across to that position. So I've got 3 zeros, then a 1, and then a 0 on here. And then remember, we pad with zeros. Binary pattern after the shift. So that's 0, 1, 0, 0, and then 4 zeros. Have we lost any precision, as in have any ones disappeared off? No. As an extension, I'd rather like you to convert these to denary and to see what the values are. So let's have a look. This value, we put the bit values on, 1, 2, 4, 8, 16, 32, 64, and 128. This one is just 8, and this one is 64. So shifting left 3 times, what's that done? Well, we've doubled 8, we've doubled it to get to 16, we've doubled it again to get to 32, and we've doubled it again to get to 64. So a logical shift left 3 times is the same as multiplying by 2, 4, 8. So is that right? 2 to the power 3 is 2 times 2 times 2, which is 8. So we've raced through this today. I really want you to focus on practicing this and getting this right. But if you reach the extension, we learnt about string manipulation last week in the Python lesson. So you know how to access individual characters within a string. You can use that to make a program that will let you shift left or shift right. So your extension is to write a program that asks you to enter an 8-bit binary number. So you type in like 000, 01, blah, 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 blah. It should then shift that left by 1 space. So you don't actually need to do the denary conversion, although I'd like you to attempt to if you get that far. All you need to do is get the substring and concatenate on a 0 in the right place. It's a nice little activity in string manipulation. If we get time, I'll try and work through a worked solution, but that's your extension. Do remember to submit your Word document. We've still got a few people who submit before they save. So save it first at the end of the lesson, close it, and then submit onto the Data 2 section on the VLE. So we have some code that works from a student, and it's fab, well done. Let's test it. So if we have 0001 and then 4 zeros, so an 8-bit binary number, and it should shift it left by 1 space. So we did have 3 zeros. We've now got 2 zeros in front. And is it still an 8-bit number? Has it still got 8 zeros or 1s? Yep, it works perfectly. So that's fab, well done. How on earth does this work? Well, we ask the question with input. Input returns a string, as in characters. And then like we talked about last lesson in Python, you can access different characters with an indexing expression. So this indexing expression means we don't start at the beginning, that would be a 0. We start the second character all the way up to the end. And actually, we could have done it shorthand with just a 1 colon, which would mean go up to the end. So 1, 1, 1, 1, 0, 0, 0, 0. If we shift that across, we lose some precision. One of those ones has disappeared off to the edge, so we've only got 3 of them instead of 4 of them. If we want to convert them both to denary, then we're going to have to use a built-in function to Python. So we have a string called binary number. If we want to convert that from binary, as in a text string that contains binary, then we can use the int function. And the int function can take 2 parameters. We normally just take a string and then it will convert it to an integer. But we can also say the base, as in if you say that this string is in base 2, binary, then hopefully it will convert it to its denary value. So let's say print help that number is, and then that value in denary. Hopefully that will convert it. So let's try something that we know. If we do 128, 1 and then 7 zeros, 1, 2, 3, 4, 5, 6, 7, it says that number is 128 in denary. So I'm not going to do everything for you. Using this built-in int function, with two parameters, the thing you want to convert to an integer and the base, as in 2 for binary. Or we could have done 16 for hexadecimal if you're really interested. I'd also like you to do the same for the final number after you've done your shift, and you should hopefully see that you can multiply by 2 if you shift across one space to the left. So that's it for today. We're just going to wrap up. We've still got 15 minutes left of the lesson to work through each of those challenges. Remember, try and do activity 1, 2 and 3. Then try and write a program that will ask you to enter in an 8-bit binary number and shift to the left. And if possible, try and convert the thing the user typed in originally and the one that's been shifted across to the left, both of those to denary. But I'll just summarize and then make sure you save your Word document and upload it to the data section on Year 10 Autumn 2. So we want to be able to apply logical left and right shifts to binary integers. An integer means integer means a whole number, binary means zeros and ones, and a logical shift, remember, only works with unsigned integers. Going left one position means that you multiply by 2. Going right one position means that you divide by 2. If a 1 disappears off to the left, then you've lost some precision, as in the number you're trying to store is too big to store in your 8 bits. So it'll go from, like, if you try and shift 128 across to the left, it should be 256, which is too big, and you'll end up with 0. If you try and shift something to the right and you lose a 1, you lose precision, because let's say if you try and divide 3 by 2, that's binary 1, 1, shifted across to the right becomes just binary 1. So 3 divided by 2 is 1.5. But 3 logically shifted to the right is just 1. You've lost some precision. Key thing to remember if you're shifting with your logical shifts is you always pad with zeros on the left and on the right. So well done. Make sure your work is saved. Get it submitted onto the VLE. We've still got 10 minutes left of this lesson.